A single crimson point. That's all James Webb saw. Not a spiral galaxy, not a glowing cloud, not even a shape you could recognize. Just a handful of deep red pixels buried inside one of the most detailed images ever taken of the universe. Around it, thousands of galaxies drift across the darkness. Some stretch into pale arcs, others reveal faint spiral arms. A few fade into soft, golden smudges at the edge of visibility. This object does none of that. It barely looks like an object at all. Now place a second image beside the first. The original was taken through a shorter infrared filter. The crimson point is almost gone. The second was captured at a longer infrared wavelength. Now it stands out immediately. Nothing in the sky moved. James Webb never changed its aim. Only the wavelength changed. That single comparison was enough to stop astronomers in their tracks. When light disappears in one infrared filter and returns in another, it often means the object is unimaginably distant. Over billions of years, the expansion of the universe stretches its light into longer wavelengths. Webb was built to find exactly that signal. Then another crimson point appeared. Then another. They surfaced in completely different parts of the telescope's deepest surveys. Tiny, isolated, and all carrying the same strange color. The headlines followed quickly. These little red points look like some of the earliest massive galaxies ever seen. They seem to come from an era when the universe was only beginning to assemble its first large structures. It felt like the opening page of a new chapter in cosmic history. Hold one of those crimson points on the screen. Now replace the image with its spectrum. The dot disappears. Its light unfolds into a long horizontal band. Most of it is smooth. Then one bright hydrogen feature spreads far wider than expected. Nothing in the photograph hinted at that. The spectrum did. A second little red dot is measured. Its hydrogen line is broad too. Then a third. The same pattern appears again. And again. Return to the original image. Those few crimson pixels haven't changed. They look exactly as they did the day James Webb first recorded them. But confidence in what they represented already has. The telescope found the objects. The measurements began questioning their identity. That is where this investigation truly starts. At first, the simplest explanation was also the strongest. Everything pointed toward extraordinary distance. Return to the two filter images. The little red dot almost disappears at shorter infrared wavelengths. It comes back at longer ones. Astronomers had seen this pattern before. As light travels across an expanding universe, its shorter wavelengths are stretched into the infrared. Objects that vanish in one filter and reappear in another are often among the oldest and most distant ever observed. The little red dots fit that picture almost perfectly. Their colors suggested great distance. Great distance suggested the early universe. And the early universe made the discovery feel entirely believable. Now zoom out. One crimson point becomes 10. 10 become dozens. Across James Webb's deep field surveys, the same tiny red sources keep appearing. Bright enough to notice, so compact they refuse to reveal any structure. No spiral arms. No extended disks. No broad halo of starlight. At first, that wasn't a problem. The earliest galaxies were expected to be small. Looking back more than 13 billion years means looking at systems that hadn't yet grown into the giant galaxies we see today. Everything still fit. The images matched the colors. The colors matched the distance. The distance matched the history of the young universe. For a brief moment, every piece of evidence pointed the same way. Then another instrument took over. Instead of measuring brightness through a handful of filters, James Webb's near-infrared spectrograph split the light into thousands of individual wavelengths. The crimson point vanished. Its fingerprint remained. Place the spectrum of an ordinary young galaxy beside that of a little red dot. Both show glowing hydrogen. One rises into a narrow peak. The other spreads into a broad ridge. That difference isn't cosmetic. It's a measurement. The width of a hydrogen line tells astronomers how fast the gas is moving. The broader the line, the faster that gas must be traveling. For several little red dots, those speeds reached thousands of kilometers every second. That's not impossible. But it is difficult to reconcile with an object that looks so calm and compact in the original image. Hold both observations together. On one side, a tiny crimson point that seems almost ordinary. On the other, a spectrum revealing extraordinary motion hidden inside that same point of light. Neither observation cancels the other. Both are real. The photograph still supports the original interpretation. The spectrum has started placing limits on it. One unusual measurement wasn't enough to abandon the galaxy model. But for the first time, astronomers were asking a different question. Not just how far away these objects were. What kind of object could produce both observations at the same time? One unusual spectrum could still be an exception. Two might justify caution. An entire population behaving the same way demanded something else. James Webb went back to the sky. Not to the same field. To different ones. The CEERS survey found more little red dots. JADES found them again. Cosmos Webb revealed another population. Uncover added even more. The telescope wasn't revisiting one remarkable object anymore. It was finding the same kind of object in completely different regions of the universe. Place the four deep fields side by side. Everything around the crimson points changes. The surrounding galaxies, the foreground stars, the observing dates, even the research teams. The tiny red sources barely do. Each remains incredibly compact. Each shines brightest at longer infrared wavelengths. Each occupies only a tiny patch of the image. The pattern has escaped the original discovery. It now belongs to the sky itself. The spectra return. Not one. Dozens. Again, the hydrogen lines are unusually broad. Again, the gas appears to be moving at extraordinary speed. Again, the source creating that signal is almost unresolved in the image. Different teams analyze the data independently. Different software pipelines reach nearly identical measurements. Different journals publish strikingly similar conclusions. The anomaly survives every repeat test. Astronomers began with the simplest possibilities. Perhaps James Webb's instruments introduced a subtle calibration error. Perhaps one observing program processed the data differently. Perhaps these weren't distant galaxies at all. Maybe they were faint stars much closer to home. The sky answered those ideas one by one. Nearby stars slowly shift against the distant universe as Earth moves around the sun. The little red dots did not. Their positions stayed fixed. Their spectra stayed consistent. Their colors stayed the same. The easiest explanations quietly disappeared. Return to the original photograph. Now mark every confirmed little red dot. One marker appears. Then another. Soon the image is dotted with tiny crimson labels. These aren't isolated curiosities anymore. They're a newly recognized population. Now compare one of them with an ordinary young galaxy. Both belong to the early universe. Only one spreads its light across a visible structure. The other compresses almost everything into a source smaller than roughly 100 parsecs. Place their spectra beneath the images. The ordinary galaxy records the slower motions astronomers expect. The little red dot repeatedly records gas racing through space at thousands of kilometers every second. Neither observation proves the original galaxy interpretation is wrong. Together, though, they become harder to ignore. The first model still explains the colors. It still explains the distance. It even explains why James Webb found these objects in the first place. What it no longer explains comfortably is something else. Why so many of them look almost identical? Why they remain extraordinarily compact? And why they keep producing the same energetic spectra no matter where astronomers search. The pressure isn't coming from one surprising measurement anymore. It's coming from all of them agreeing. Hold the original little red dot on the screen. Keep its spectrum beneath it. Now add one more measurement. Its total brightness. Astronomers asked a question that sounded almost too simple. If every photon reaching James Webb comes from ordinary stars, how many stars have to fit inside that tiny crimson point? The first estimates produced an uncomfortable answer. Several little red dots appeared to contain tens of billions of solar masses worth of stars. Even today, that would describe a substantial galaxy. Return to the image. Nothing about it suggests a system that massive. The source is still unresolved. Its light still comes from a region smaller than roughly 100 parsecs. Now place those two measurements together. The brightness demands an enormous population of stars. The size leaves them almost nowhere to fit. The contradiction is no longer hiding inside the spectrum. It appears the moment the image and the brightness are considered together. Add one more comparison. On one graph, plot the age of the universe. On another, plot the amount of stellar mass required by the ordinary galaxy interpretation. The little red dots land in a region where galaxies were never expected to exist. Not simply because they're early, because they already appear too mature, too massive, too concentrated. Not because James Webb measured impossible numbers. Because the ordinary galaxy model has to satisfy every one of those measurements at the same time. Astronomers tried to save that first explanation. Perhaps the stars were much younger than originally assumed. Young stars shine more brightly. If so, fewer of them would be needed. The estimated mass dropped, but not enough. Another correction followed. Perhaps thick dust had altered the colors. Accounting for that dust reduced the stellar mass again. The tension eased. It never disappeared. Each adjustment solved one part of the puzzle. None solved the whole puzzle. Return to the spectrum. The broad hydrogen line is still there. Return to the image. The compact source is still there. Return to the mass estimate. It's still uncomfortably high. Each measurement continues pointing in the same direction. The problem is no longer any single observation. It's the combined weight of all of them. Something about the original interpretation is beginning to fail. Not because one measurement overturned it. Because every measurement now has to be true at the same time. This is the point where the investigation quietly changes direction. Astronomers stop asking how an ordinary galaxy could have formed so quickly. They begin asking a different question. What if they have misidentified the brightest source of the light? The little red dot still occupies the same handful of pixels. Nothing about the image has changed. Only the label attached to those pixels has begun to loosen. The first model hasn't been disproven, but it has reached the point where every new measurement demands another exception. Whatever these crimson points are, they seem able to produce far more light from far less space than ordinary galaxies comfortably can. The next reconstruction doesn't begin with another image. It begins by changing a single assumption. Keep every measurement. Keep the same photograph. Keep the same spectrum. Change only one thing: the source of the light. Instead of asking how billions of stars could fit inside such a tiny region, astronomers considered another possibility. Suppose much of that light doesn't come from stars at all. Suppose it comes from gas falling toward a rapidly growing supermassive black hole hidden inside a young galaxy. The photograph doesn't change. The interpretation does. Lay that reconstruction over the original image. The compact size is no longer surprising. A black hole doesn't need an enormous galaxy to produce enormous amounts of light. As gas spirals inward, gravity compresses it, heats it, and accelerates it to extraordinary speeds before it disappears beyond the event horizon. Long before that happens, the gas releases tremendous energy. Most of that energy never reaches James Webb directly. Dense clouds of dust surround the central region. They absorb the intense radiation. The dust heats up. Then it shines again in the infrared. The tiny crimson point remains exactly where it was. Only now, much of its brightness no longer has to come from stars. Return to the spectrum. The broad hydrogen line hasn't changed either. This time, it tells a different story. Instead of asking how ordinary stars could push gas to thousands of kilometers every second, that same measurement naturally fits gas orbiting much closer to an extremely massive central object. The evidence is identical. Only the explanation is different. Now compare the two reconstructions. The first asks ordinary stars to explain the object's brightness, its compact size, and its energetic spectrum all at once. The second allows a hidden central engine to generate much of the light while the surrounding young galaxy contributes the rest. Neither explanation is perfect, but one demands far fewer compromises. That difference became harder to ignore with every new observation. Independent research groups approached the problem from different angles. Some modeled the infrared colors. Others reconstructed the spectral energy distribution. Others compared the compact shapes with known active galactic nuclei. The methods differed. The direction did not. Again and again, the hidden black hole reconstruction accounted for more of the evidence than the ordinary galaxy model. Return once more to the original little red dot. It's still nothing more than a tiny crimson point. The pixels reveal no black hole, no glowing accretion disk, no dramatic jet. Nothing in the image tells you which explanation is right. The measurements do, not because they've proven every detail. Because one reconstruction keeps surviving tests that the other increasingly struggles to pass. For now, it stands as the strongest explanation, not the final one. One small feature in the spectrum still refuses to fit perfectly. Ironically, the same data that helped build the new model also reminds astronomers that it remains unfinished. The final observation doesn't overturn the hidden black hole picture. It limits it. Return to the spectrum one last time. The broad hydrogen line is still there. The compact source is still there. The deep infrared glow is still there. Together, they continue pointing toward a heavily obscured central engine buried inside a very young galaxy. But another feature refuses to disappear. At shorter wavelengths, a faint trace of blue and ultraviolet light still escapes. Instead of fading smoothly from blue into deep red, the spectrum bends into a shallow V. The image stays silent. The spectrum does not. It says there's still another piece of the puzzle waiting to be explained. Astronomers haven't ignored that mismatch. One possibility is that the dust surrounding the black hole isn't a smooth, continuous shell. It may be clumpy. If that's true, narrow gaps could allow small amounts of blue and ultraviolet light to escape without exposing the central engine itself. Another idea reaches the same goal a different way. Instead of escaping directly, some of that energetic light may scatter off nearby gas before traveling toward James Webb. Both scenarios reproduce much of what the telescope sees. Neither explains every detail. The hidden black hole model remains exactly what it has become through the evidence. The strongest reconstruction, not the final one. Now remove the graphs. Remove the spectrum. Remove the mass estimates. Return to the image that opened this investigation. A tiny crimson point. No larger than a handful of pixels. It has never changed. The same photons reached James Webb on the first day. They reach us the same way now. The colors are unchanged. The brightness is unchanged. The shape is unchanged. Only our understanding has moved. At first, the object looked like one of the earliest massive galaxies ever discovered. Then its spectrum challenged that identity. Independent observations repeated the contradiction. The combination of extreme brightness and extraordinary compactness pushed the original explanation to its limit. A dust-shrouded supermassive black hole growing inside a young galaxy gradually became the interpretation that survives the greatest amount of evidence. Even that picture remains unfinished. The object has not reached the end of its story. Only the edge of our current evidence. Perhaps that's the most remarkable thing about the little red dots. James Webb didn't simply reveal a new class of objects. It revealed something just as valuable. How scientific knowledge actually grows. It begins with light. A name comes next. Then the measurements arrive. Some ideas survive. Others don't. The names change. The photons never do. The little red dot remains exactly where this investigation first found it. Still a tiny crimson point. Still almost invisible in one filter. Still glowing in another. Still asking the same quiet question. Not what it looks like, but what it truly is.